Hello and welcome back to another lecture on linear algebra. This is going to be pretty much of a wrapping up lecture, even though I'm going to introduce a new concept. And the new concept, of course, is the one of Euclidean vectors. Our good old friend Euclid, the ancient Greek mathematician and philosopher, is behind some of the ideas here and there. That's why we talk about these vectors as being Euclidean. But I'm not going to go there. I'm not going to explain to you what I'm not going to discuss what is the connection between good old Euclid and these vectors. Okay, but this is pretty much what we're going to do today is just But what we're going to do today is pretty much just an extension of what we've been doing in the first few classes. So we're going to be using the start with this idea of vectors and extend it beyond what we have seen so far in terms of geometric vectors. All right. So what this thing is going to be our first attempt at a major generalization. Okay. But it's a simple one, so we should be able to handle it very easily and quickly. Okay. So what is a Euclidean vector? Well, a Euclidean vector is an ordered set of n real numbers. Remember, for geometric vectors, it was an ordered set of either 2 or 3. Well, we can keep going. So it's a set of n real numbers, where n is a natural number, which is called the dimension of the vector. Let me give you some basic examples of what a Euclidean vector looks like. Okay? So for instance, for n equal 4, well, here is a 4-dimensional vector. It's just a set, an ordered set of 4 numbers, 4 real numbers, 4 real scalars, which of course, as you remember, are called the components of the vector. Okay? For n equal 5, well, here's another one. Nothing new about it, it's just one more component. Okay? For n equals 6, well, it just gets longer. Nothing very much more complicated. I'm throwing in some weird numbers just to remind you that we can use any real numbers, be they integer, fractions, irrational, whatever. Okay? And for n equals 3, well, here is a 3-dimensional Euclidean vector. And that looks very familiar because, of course, that is also a geometric vector. In fact, all geometric vectors are Euclidean vectors too. N could be 2 or 3. In fact, it can also be 1, but then the thing becomes a little bit useless. However, keep in mind that other Euclidean vectors are difficult to visualize. The geometric ones, of course, they're relatively easy, especially the 2-dimensional ones. The 3-dimensional ones are easy to visualize, difficult to draw. But once we go into 4 dimensions and higher, they're very difficult to visualize. So in fact, we're not going to visualize them. Remember, we are going to generalize into the algebraic realm. So we're going to look at these things as algebraic objects, but at the same time, we're going to try and keep our basic model of geometric vectors to understand some of the things that we're going to do with these vectors. So what kind of things are we going to do with Euclidean vectors? Well, what can we do? Well, pretty much everything we have done so far with geometric vectors. For instance, we can add them. Okay, so if I give you 2 vectors, v, whose components is going to be v1, v2, vn, and w, or components w1, w2, wn, and of course they have to be of the same dimension. Okay. Oh, by the way, some people also talk about the dimension in reference to the dimension. They say this is the size of the vector. Okay, so we can say that these are 2 n-dimensional vectors, or 2 vectors of dimension n. Well, we can add them up in the obvious way. We're going to add up the first 2 components, the second 2 components, the third 2 components, and so on until we have added them all up. And of course, it is not any more complicated to define a scalar product. So if we have an n-dimensional vector and a scalar, the product of the scalar and the vector is just obtained by multiplying the scalar by each of the components. And of course, once we have an addition and a scalar product, we can define a linear combination. So if we have a whole bunch of vectors, v1, v2, vm, now notice m is a different number, not the same necessarily as n. N in this notation is the dimension of the vector. M is how many vectors we actually have. You can multiply each of them by a scalar and then add them up. So again, nothing really much more complicated, just longer, but not more complicated. We can also define a dot product. Remember, the dot product was defined purely algebraically. What we do, given 2 vectors, is we multiply the first 2 components, and then we add to them, to that product, the product of the second 2, and then the product of the third 2, and so on, until we have exhausted all the components. So all of these things are pretty duh, and I'm sure they're not going to create any difficulty for you. Let's see what else we can do with vectors.